Welcome to the CopperSpice YouTube channel, and thanks for joining us. In this video, we are going to talk about map containers and how to select the correct one. A guide to maps. In order to understand and ultimately select the best map container for a given application or use case, it is important to know our options. This involves looking at the data structures they use internally. We will do this by taking a brief look at binary trees and hash tables. Although the standard library does not currently provide a FlatMap container, there are several existing implementations. Any discussion about map containers should also include FlatMap as one of the options. When looking at selecting the right map, there are a variety of factors to consider. We will talk about the general guidelines you should think about and if there really is a one-size-fits-all container. A large part of computer science is the study of data structures. These are the building blocks for storing data in some organized or maybe even unordered way. The binary tree is commonly used to implement the map container. The word binary in the context of a tree means that each node has no more than two children. When the nodes in a binary tree are maintained in a sorted order, then walking the tree, starting from the root, provides a quick way to find or locate the node with a given key. There are different types of binary trees, such as full, complete, and balanced. When implementing a map using a balanced binary tree, this increases efficiency. There are actually several categories of balanced binary trees. Two of the most common are the red-black tree and the AVL tree. The name AVL is not actually an acronym. It simply refers to the names of the two inventors. There is another way to implement a map if the data does not need to be maintained in a sorted key order. The hash table data structure is commonly used to implement an unordered map. The elements of a hash table are divided and stored in what are called buckets. Each bucket holds 0 or more elements. Which bucket a particular element belongs in is determined by a hash function. For both the binary tree and hash table, the idea of inserting elements is valid and supported. Appending an element does not actually make sense, since the tree is sorted, so the element may not belong at the end. For a hash table, the element's location is in a specific bucket, not necessarily the last bucket. We wanted to mention that in functional programming, when developers refer to a map, they're talking about a map function and not a map container. In languages like Haskell, a map function is used to operate on a container and produce a new container as the output. For comparison, the algorithm std transform in C++ is very similar to the map function in functional programming.
These are the two containers in the C++ standard library which use a balanced binary tree data structure. The std map container stores a given key with a corresponding value. The keys are used to sort the map. An std map is not allowed to have duplicate keys. And since the map is sorted, an iterator can be used to walk from the beginning to the end of the map. All of the elements will be in ascending order by key. The return value for a call to the insert method is an std pair containing an iterator to the element and a bool indicating if the insert succeeded. If you call insert and the key already exists, the call actually does nothing, and the bool in the returned pair will be false. The other binary tree container is std multimap, and the main difference is that you can have duplicate keys. Calling insert on an std multimap will never fail. The new key value pair is always added, and the return data type is only an iterator to the new element, not a pair. In C++17, a new method called insert or assign was added for stdmap. Calling this new method when the key already exists will update the value for the given key. The return value for this method is oddly still a pair. The bool will be true if the data value is added, and false if the value is assigned. Several years ago, when we refactored the containers in CopperSpice, we switched from using hand-rolled containers to leveraging the existing ones in the standard library. We made the tough choice to keep the existing API for the insert method in QMap. This method returns only an iterator, and the functionality is equivalent to the insert or assign method in stdmap. There are two other containers in the C++ standard library which use a hash table to implement std unordered map and std unordered multimap. Incrementing an iterator from the beginning to the end of the container will walk every element. However, since the containers are unordered, the elements will be seen in a random order. In the unordered map container, each key corresponds to a single value, and there cannot be duplicate keys. The underlying structure for a hash table is an array. One of the interesting things about the unordered map is that a hash table will become slow if the array is nearly full. The load factor method can be used to query the data structure and find out how full the array currently is. Normally this will not be required, since the hash table will grow automatically. The std unordered multimap is very similar, except this container allows duplicate keys. If you have an unordered multimap with a large number of duplicate keys, this container may not be a good choice. Every duplicate key will cause a hash collision and slow down all the operations. Both the std unordered multimap and std multimap containers have a method called equal range. This method returns a pair of iterators, so you can efficiently access all matching elements for one specific key.
There is one other map container we want to mention, although it is not currently part of the C++ standard library. It is called FlatMap, and it is usually implemented using a vector data structure, where the t, or the element type, is a pair. The vector is always kept sorted by the key, which is the first value in the pair. Most implementations of a FlatMap will have an API which is very similar to stdmap. The reason this map is attractive has to do with the speed and low memory consumption. When your data set is quite small, usually below a few hundred elements, the FlatMap container can be very fast. There is no memory overhead, since there is no need to store the pointers for binary tree nodes or the empty space used for optimization in a hash table. There are several different C++ implementations of FlatMap in third-party libraries. The FlatMap container in the Boost libraries has been available since 2011. This implementation is somewhat awkward since it still supports pre-2011 compilers. We added the QFlatMap class to CopperSpice to support our documentation application. As DoxyPress is parsing the source code, it needs to store a small number of attributes for each class or function. Storing this data in multiple small flat maps turned out to be very efficient and easy to understand. The alternative would be a massive map which has a compound key, and this would be complicated to implement. As a side note, Qt does not offer support for the QFlatMap container. There is a proposal to add a FlatMap container to the standard library. However, it was not added to C++20. There are some open questions about the best implementation, and we believe the committee is still working on a design.
A very common question we hear is, how do I pick the right map container? There is no quick answer, and it really depends on the data and needs of the application. The solution is to evaluate and consider what parameters are most important to satisfy your requirements. One of the factors to decide is whether speed or memory is more important to your situation. If speed is the most critical, then an unordered map is the best choice. If you can determine that your map will be relatively small and the key is not too complex, a flat map is even better to satisfy the requirement for speed and provides the added benefit of using less memory. If the flat map may occasionally grow to an extremely large size, be aware the speed will suffer at these times. If your target involves both speed and memory, you will need to decide which is more important and maybe benchmark to find the right balance. If the map may grow and shrink repeatedly by thousands of elements, choosing one of the binary tree-based containers will be the better choice, since they can release memory as the elements are removed. These are the ordered map containers. In comparison, the hash table and vector-based containers will grow when they become full, but will not shrink when entries are erased. If you need to insert elements while you're iterating over the container, then an ordered map is the only valid choice. The insert method for an unordered map will invalidate iterators, so once you do the first insert, your position is unknown. Calling the find method to locate an element in an ordered map involves a binary tree search. Starting from the root, the key is compared to each node to decide whether to travel left or right. For a map with more elements, more comparisons will be required to find the correct node. For an unordered map, we are searching in a hash table. This is done by calling a hash function to determine the correct hash bucket to search in. Then each element in the bucket is compared with the specified key. Since the number of items in each bucket is normally small, the number of comparisons will stay roughly constant even as the container grows. If the only consideration for choosing a map is the find operation, then having a sorted container is not necessary. If this is your scenario, choosing an unordered map will be the right choice. One important point to mention is the key must be a hashable data type. This requires finding a hash function which is fast and produces few collisions. Since there is no map container which is right for every situation, the idea is to make the best choice possible. Since the API is very similar between the map containers, be willing to experiment and see if choosing a different map will improve the performance of your application. For more information about the CopperSpice project, please visit our website at www.copperspice.com.
Thanks for watching. We hope you found the content of value. If you have any questions or feedback, feel free to leave a comment on this video or send us an email.
Please make sure you subscribe to our YouTube channel and come back in a few weeks for our next video.